Today we begin section 7.2, and as you can see by my title there, we're going to be multiplying and dividing radical expressions. And what I'm going to actually do is divide this lesson up into two parts. So this particular video will just be considered part one, and all we're going to do is look at multiplying radical expressions. And then there'll be a separate video, part two, will look into dividing. So even though it's one section, we're going to divide it up into two separate video lessons. So what I've provided for you here in blue is our, I guess you could say, principle that determines whether or not two radicals can be multiplied together. And it basically says these two things, just in paraphrasing what I have written here. In order for two radicals to be possible to multiply together, number one, they have to have the same root, or this little n refers to a number called the index. And if these are square roots, then we don't show the actual number when we write the radical, but we understand that that number n in this case would be 2. So number one, in order to multiply radicals, the index, or the root, in this case the letter n, has to be the same. Square root times square root, fourth root times fourth root, and so forth. And then the other thing that has to be true is that the radicals have to represent real numbers. And if those two conditions are met, then we simply multiply the numbers underneath the radicals to come up with our product in radical form. So my green question to you is, this expression, or this multiplication, is not possible because the reason is the square root of -5 is not real, and that's one of our conditions. These radicals have to represent real numbers. And therefore, since the square root of -5 is not a real number, then if this were a homework problem, you would just say not possible. Okay, so that leads us to some examples like you will do on your homework on the first set of problems. You're told to multiply, and then you're told to simplify if possible. So, as you can see by our instructions, we're told to multiply if possible, and we just looked at how we can know if multiplication is possible. And then if we can, we will simplify the product. So, taking a look at letter A, in letter A, we notice that the roots, or the indices, are the same, so that checks out. Both of these radicals represent real numbers, so we're good to go as far as multiplying these two radicals together. And if we do, we just do the radical, the square root of 3 times 12, which is 36. And then we recognize that 36 is a perfect square root number, and the square root of 36 is 6. Okay, looking at letter B, we check out the indices. They are the same. We notice that we have real numbers here, and this has been a little bit of caused a little bit of trouble for certain people today because they notice that we have a negative number underneath the radical. Well, the question here is this: since we're dealing with a cube root, what that means is we have a certain number being multiplied times itself 3 times. Well, in general, is it possible to know whether or not a radical represents a real number? Let's think about this. Is it possible to have the same number times itself 3 times and equal a negative result? Okay, well, certainly it is, because let's just take, for example, the number -3. If I multiply -3 times itself 3 times, I get -27. So in general, what we're saying here is, for odd numbered roots, it's perfectly fine to have a negative number underneath the radical. That represents a real number. Well, let's just see the example provided for us here in letter C. This is an even number root. It's a square root, so really there's an invisible 2 sitting in that little slot. And what it says is it possible, since it's a square root, can we take the same number times itself and get a negative result, like negative 16? Well, that is not possible. Anytime you multiply a number times itself, the result should always be positive. So letter C gives us an example of two radicals that cannot be multiplied together, because even though they have the same roots, you have an expression, one of the radicals represents an expression that's not real. Okay, so jumping back up to letter B, we established that we can multiply these together, remember, because the root or the index is an odd number. It doesn't really matter if the number underneath is positive or negative. So we get the cube root of negative 64, and there is a number that would multiply times itself 3 times to equal negative 64, and that's the number negative 4. Okay, so that's a lot of what you're going to do on the first set of problems in the homework. All right, jumping down to the next set of problems, some examples to help you with these. The instructions tell us to simplify the expression. So the way I want you to do this is to show multiplication. In other words, I want you to think of two radicals that would multiply together to equal the given radical in the problem, in this case the square root of 50x to the 5th. But here's the catch. When I write these two radicals, one of them, if possible, and it is, needs to contain only perfect square root numbers or variables. Numbers or variables that have perfect square roots. The other radical, in my case the one on the right, will contain expressions, numbers, variables that do not have perfect square roots. They cannot be simplified by taking the square root of the number or the variable. Okay, so to begin with, I need to think of the number 50, and I'm trying to come up with a perfect square root number that divides evenly into 50. And I come up with the number 25 that has a perfect square root, and it also divides into 50. And so to make this equal 50 when multiplied, obviously I'm going to have to say that it's going to be multiplied times the square root of 2. These two together would equal the square root of 50. Okay, so let me just back up for a minute and make sure you understand this. There are some other combinations or factors of 50. Say, for example, I could have said the square root of 10 times the square root of 5. The problem with this is I'm supposed to simplify this. In other words, try to get as much of this written without a radical as possible. The problem with these numbers is neither one of them are perfect square roots, so I can't simplify either the square root of 10 or the square root of 5. I have to leave them in radical form. However, if I go back to my other example, if I show it as the square root of 25 and the square root of 2, at least one of these can be written without a radical, because the square root of 25 is just regular number 5. So that's the goal, to try to get as much of this number written without a radical as possible. That's really another way of saying simplify. Okay, so let's move on to the variable. Remember, for square roots, there's an invisible 2 sitting in this slot. Okay, we don't show it for square roots, but we understand that it's there. So here's the way I go about simplifying variables underneath radicals. I take the index, which in this case is 2, and I see if the index divides into the exponent, in this case 5. Well, 2 does not divide into 5 evenly. So I'm trying to find an exponent less than 5 that is divisible by 2. Okay? And I want to try to find the biggest one I can, because remember, I'm trying to get as much of this expression out from underneath the radical as I can. So what about x to the 4th? That works because 2 divides into 4 evenly. But to make it equal x to the 5th when multiplied, I'm going to have to put x to the 1st over here on this right radical that represents imperfect square roots. Okay, so just a quick double check. Do my two radicals multiplied together equal the given radical? And the answer is yes. So this left radical can be simplified. The square root of 25 is 5. And the way I simplify variables underneath these radicals is I just divide. Take the 2, divide into 4, and that gives me the exponent for x. 4 divided by 2 is 2. And this right radical stays in radical form because there is no perfect square root of 2 and there is no perfect square root of x to the 1st. That's my answer for letter A. Okay, letter B, much the same, except notice, pay close attention to your roots or the index. This time we're dealing with cube roots, so I'm asking the question, is there a perfect cube root of 54? Is there a number that multiplies times itself 3 times and equals 54? And the answer is no. So I'm going to write this as the product of 2 cube roots, one of which should represent all perfect cube numbers. The other one will represent all non-perfect cube numbers and variables. Okay? So just a quick look, you'll probably do yourself a favor to familiarize yourself with the perfect cube numbers. Now, I'm not counting 1 because obviously 1 to the 3rd power is still 1. But let's take a look at some of the perfect cube numbers. 8 is a perfect cube number. The cube root is 2. 27 is a perfect cube number. The cube root is 3. 64 is a perfect cube root number. The cube root is 4. 125 is a perfect cube root number. The cube root is 5. So you really, for the most part, I can't imagine going any higher than that, but you get the idea. If you just kept going using your calculator, you can get more numbers that are perfect cubes. So right off the bat, I noticed that the perfect cube root number 27 divides into 54 evenly, and 27 times 2 equals 54. Okay, so for the variable n raised to the 8th power, unfortunately 3 doesn't divide into 8 evenly. So n to the 8th is not a perfect cube variable expression. So the next best thing I can do is say, well, what about n to the 6th? 6 is less than 8, and it's also divisible by 3. But to make it equal n to the 8th when multiplied, I'm going to have to multiply by n to the 2nd. Alright, so we're almost there. The cube root of 27 is 3. To get the cube root of n to the 6th, just think of n to the 6th divided by 3 power. 6 divided by 3 is 2. And the rest of this radical stays in radical form because I cannot simplify. But we did quite a bit. We changed it from this larger expression and we got it reduced quite a bit, simplified quite a bit. Okay, same thought here with the cube root. 80, looking at my list, is not a perfect cube root number. It doesn't have a perfect cube root. But I noticed that 8 is a perfect cube root number, and it also happens to divide into 80. So I'm going to rewrite this as the cube root of 8, and to make it equal 80 when multiplied, I'm going to have to do the cube root of 10. Okay, so for n to the 5th power, unfortunately 3 doesn't divide into 5 evenly, but 3 does divide into 3 evenly. So the number smaller than 5 that divides into 3 is 3, which means to make it equal n to the 5th, when multiplied, I'm going to multiply by n to the 2nd. Okay, focus on this left radical. The cube root of 8 is 2. The cube root of n to the 3rd is n. And the rest of this stays in radical form. Okay, let me circle my answers here. Letter D, 18, not a perfect cube root number. And also notice that I don't have a perfect cube root number that divides into 18. Interesting. So when I set up my two radical factors, I'm going to have to put 18 over here with the group that is not perfect. There is no perfect root, cube root, and there's no perfect cube root factor. Okay, so let's focus on x to the 4th. 3 doesn't divide into 4 evenly, but 3 does divide into 3 evenly. And I can put x to the 1st over here so that when multiplied together, just keep in mind these two radicals that you come up with have to multiply together to equal the one that's given. Okay, so this one's pretty easy. The cube root of x to the 3rd is x, and we'll be multiplying, just erase this, we'll be multiplying times the cube root of 18x. Alright, let's try one more. This is a square root. Always good to pay attention to the root that you're dealing with. And unfortunately, the 8 is not a perfect square number. It doesn't have a perfect square root. So let's think of two radical factors, two square root factors that would give me 8. So the square root number that divides into 8 evenly is 4. And times square root of 2. 2, this invisible 2, does not divide into 5 evenly, but it does divide into 4, so it's the next best thing, x to the 4th, which means over here I'm going to put x to the 1st, simplify the left radical, square root of 4 is 2, square root of x to the 4th is x squared, and show the rest of this as being multiplied together. Okay. All right, one more section, and this will conclude this video, and this is what you're going to do on 18 through 22. The first thing we're going to do is take the two radicals that were given and multiply them together. So the square root, notice these are both square roots, so we can multiply. They both represent real numbers. So 18 times 2 is 36. When I multiply x to the 3rd times x to the 2nd, I just do x and then add the exponents together. And then I've got this y to the 3rd. Alright, well, we're back now to what we were doing on the previous slide. We need to simplify this, so think of your two radical factors and start with the number. As it turns out, 36 is already a perfect square number, so I'll put it with the perfect group. X to the 5th is not a perfect square root variable because 2 doesn't divide into 5 evenly, but I can write it as x to the 4th, which is a perfect square variable, times x to the 1st. And in a similar way with y to the 3rd, I can do y to the 2nd times y to the 1st to get y to the 3rd. Simplify the left radical. The square root of 36 is 6. Square root of x to the 4th, you just do x to the 4 divided by 2 power, and y to the 2 divided by 2 power, don't really need the 1, and then that's going to be multiplied times the right radical, which cannot be simplified. So that's my final answer for letter A. Letter B, let's multiply first, and we get the cube root of 10 times 4 is 40. X to the 4th, y to the 5th. Now again, always pay attention to the root that you're dealing with. So these are cube roots, so let's think about our cube root list again. I'm looking for a perfect cube root number that has a perfect cube root that divides into 40. Looks like that's going to be 8. Okay, so my two radical factors, I'm going to use the cube root of 8, perfect cube, times the cube root of 5, not perfect cube. That gives me the cube root of 40. Okay, 3 doesn't divide into 4 evenly, so I'm going to have to write x to the third, which is a perfect cube, times x to the first. Y to the fifth, 3 doesn't divide into 5 evenly, so I'm going to write y to the third, perfect cube, times y to the second. And now I'm going to simplify the left radical. Cube root of 8 is 2, x to the first, y to the first, times the radical that cannot be simplified, the cube root of 5xy squared. Okay, that takes us to one more problem. And so cube roots multiply together. We have the cube root of 8x to the third. Well, this is interesting because if I notice, 8 is a perfect cube root number. It has a perfect cube root, which is 2, and x to the third. 3 does divide into 3 evenly, so x to the third represents a perfect cube root variable. So I really don't have a reason to break this up into two radical factors because as it is, it can be simplified. The cube root of 8 is 2, cube root of x to the third is just x, and that ends up being my answer. Okay, so we're going to conclude this lesson, and we'll take the division part of this section in a separate video, and just contact me if you have any questions.